An important part of a communications installation is something known as the power plant. Different from the power plant known by laymen, this type of power plant is effectively the power supply system for the site or facility. For critical infrastructure with reliability measured in the number of nines, power plants need to be highly reliable and have at least one, if not several, forms of backup power. Now, let's describe the general basic operating principle of many power plants. Utility power charges battery banks, which then supply power to the connected loads. Should utility power be lost due to an outage, the batteries are typically sized for about 8 hours of runtime. Should power not return soon enough, a generator can be turned on to start recharging the batteries and keep the equipment powered. In less critical environments, this generator may not exist or may be brought to the site on a truck when needed. In more critical environments, however, this generator will be on site and will start automatically after a predefined outage duration. One might ask, why do you need the batteries if you have a generator? Two reasons. One, you need a battery to start a fossil fuel generator. Anyone with a gas car knows that. Two, that generator takes time to start. Typical industrial generators take about 10 to 30 seconds to stabilize. This general operating principle for power system redundancy remains in place today, and we'll cover that later in the video. Now, let's talk about the power plants of AT&T long lines, and specifically their TD2 microwave system. This graphic comes from an article published in the Bell Labs Record in 1952. Since batteries are inherently direct current devices, you needed rectifiers to convert the incoming AC to DC. A fun fact to note is that silicon devices could not handle this amount of power at the time. Thyratron tubes were used for the two higher voltage rectifiers, and selenium rectifiers were used for the two lower voltage ones. Note that several voltages were required to power all the equipment. The various vacuum tube amplifiers would have been powered by the 130 volt and 250 volt plate supplies. Interestingly, the 250 volt power supply is derived by adding an additional 120 volts worth of batteries in series to the 130 volt power supply. Here are some photos of the power plant equipment at the time. Now, let's talk a bit about the generators. The original generators at sites between New York and Denver were gasoline powered. Generators west of Denver, however, ran on diesel. While diesel is generally seen as the superior choice for a generator, Bell's specialized diesel engines were not complete in time to be used throughout the transcontinental link. Notably, 3 stations west of Denver were in such remote locations that bringing utility power to them was not economically feasible at the time. Instead, they each were powered by 2 diesel generators. At any given time, one was operational and the other was the standby, or backup. The 2 generators would switch roles every 12 hours to even out the wear. On this typical floor plan for a TD2 relay site, you can see where all the power plant equipment resided. Note that these battery banks took up considerable floor space. This picture is not from a TD2 site, but gives you an idea of the sheer scale of the battery banks. The original AT&T microwave network was built with vacuum tube amplifiers, which require very high voltages to operate. As time went on, the amplifiers were replaced with solid-state or transistorized devices. These solid-state amplifiers were much more reliable and power-efficient than their predecessors. They could operate at lower voltages, too, reducing the need for massive numbers of batteries connected in series. Now, let's expand upon the block diagram we showed earlier in the video. Here's a more complete block diagram for a general power redundancy system. You might have loads that require AC power, so you'll need to convert the DC from the batteries back to AC with an inverter. Should this DC subsystem fail, a bypass line can still provide power. Connecting topics now, the highlighted portion effectively represents an online uninterruptible power supply, or UPS. The term online, in this case, means that the inverter remains in use during normal operation. This is optimal in many cases, as the conversion and batteries effectively remove any disturbances in the power supply. The cheaper alternative to an online UPS is an offline or standby UPS. The load is powered by utility or generator power by default, and the inverter only switches on after main power is lost. This results in a mini power dropout in the event of main power loss. However, the switching is fast enough that most modern computer and networking equipment can handle the blip just fine. One of the main reasons why offline UPSs are cheaper is that the rectifier does not need to be sized to power the load. It only needs to charge the battery. For example, many consumer-grade UPSs can supply hundreds of watts of power during an outage, but only charge the battery at around 5 watts. A significant limitation of the offline UPS is that it must transfer to battery in the events of sustained undervoltage or overvoltage. Note that surge protectors only protect against brief voltage spikes and not sustained overvoltage events. The Line Interactive UPS was created to solve this problem. A variable tap transformer can be adjusted by control circuitry to increase or decrease the incoming voltage. This technique effectively makes the Line Interactive UPS a bit of a compromise between the more expensive online type and the cheaper offline type. Line Interactive technology is commonly found in higher-end consumer and office-grade UPSs. Now, this general template is common for a power redundancy system, whether it be for a telecommunications site, hospital, data center, or other mission-critical application. Of course, depending on the complexity of the site and the criticality of the application, you might have multiples of each device for further redundancy and segmentation. I will link the source materials used in the description of this video. I plan on continuing this series with more material I found in the Bell Labs record. As always, feel free to drop a comment if you have any insights or thoughts on something I missed.